Hello everyone, welcome to my YouTube channel. So here in this session, we'll again go with all the three softwares for the analysis, that is Abaqus, Ansys, and SolidWorks. And I'll deal with the model analysis here using the tuning fork. Okay, so this fork has the natural frequency of 443 Hertz on an average. So what I'll do is I'll do the same frequency analysis on all the softwares and just we'll see the results and compare how exactly the results are. Okay, let's start with this. Initially, I'll deal with the SolidWorks. So I'll utilize the step file. So that is tuning fork step file. So if it is step file, you need to break the links or else you need to import the diagnostics. Okay, yeah, so I'll utilize the add-in, that is SolidWorks simulation. So at this moment I'm going to deal with the frequency analysis. You can just select the same here. The material, I'll just use the apply material tab. From there you can just look for the stainless steel. There are different material data available here, so I'll go with the chrome stainless steel. See, Inks modulus is 2 into 10 raised to 5 megapascal. 0.28 is the Poisson's ratio, and 7800 is the density. Okay, so I'll simply apply the initial fixture, that is only the fixed. These two are the faces for the reference for me, and the mesh. Before that, you could see the properties, so I just need to set the number of range, the modules which I'm looking for. So I'll use the frequency range up to 10. Okay, so it will give me the 10 set of frequency range. So the meshing, I'll use the standard mesh, and 0.5 is the mesh size here. SolidWorks will deal with the tetrahedral mesh only at the moment. Okay, so this is the mesh, but fine. I'll just run the study and we'll check for the results. Okay, so agenda is to just cross check the actual frequency of this tuning fork. That's all. Yeah, so as you could see, I got the 10 amplitudes with respect to the 10 frequency ranges. Okay, you can just check these all the 10. So the frequency is 226 for the first one. Okay, and this is the mode shape. The initially this is how it gonna deflect. Okay, this is just an approximation. Okay, whatever the displacement you are seeing, this is not exactly practically it does. Okay, but practically if I see this will not be the practical application, right? The tuning for application is to hit it and just check for the frequencies. So to get that particular displacement, we might need to animate few. Okay, before that I'll use the list of resonant frequencies. I already know that the natural frequency of the tuning fork is 443 Hertz. Okay, so I had ran the study for 10 number of modes, and the last one is 4800 something, right? Yep, so at the moment I'll just check with the 10th one. So it is 4800 Hertz. So practically we'll consider the initial 4 or 5 natural frequencies because the least matters a lot. So naturally the natural frequency of any component will be the initial in between the initial 4 or 5 natural frequencies. Okay, with respect to load applications as well, it is same. And for the 10th mode, you could see this is how it gonna deform. So this is not the exact deformation which will happen in practical case, right? So yeah, so we can eliminate this frequency, that is 4807. So as I already told you, for this natural frequency, the experimented value is 443 Hertz on an average. Same thing, you can cross-check the natural frequencies of each and everything. So at the moment, I'm concerned about the fourth mode, and you could see the natural frequency of it is 443 hertz, and the we'll see the model behavior now, how exactly it's gonna behave. Yeah, so we'll create the time frame. This is how it's gonna behave. But the animation is, it is amplified, it is not the true scale. Okay, we can set it to true scales if you want. Yep, so this is about the SolidWorks workbench, the analysis which we have done. So now we'll see with the other softwares as well. Yeah, so now I'll work with the Ansys workbench to cross-validate the same by using the another software, that is again the virtual testing. Okay, I'm comparing the results with the softwares, so it is not the practical validation, it's the just virtual validation. And this might not be correct because I'm just considering the approximations and the normal meshing methods for the model. Okay, so in this Ansys workbench, I'll use the model analysis here. So you could see there are different types of analysis available, starting from structural and the model. Okay, like that. Yeah, so in the previous analysis, I had used the stainless steel as my material consideration. So here also I need to select the same material into account. So for that, you can use the engineering data. So you can edit this at the moment. So by default, we have the structural steel. Okay, the density is 7850 and the Young's modulus is 2 into 11 Pascal, and the Poisson's ratio is 0.3. But for cast, that is stainless steel, it is different. So what I'll do is I'll create the new material, just click on it and just name it. It is steel for me here. Okay, so once you do it, you can able to assign the properties for this material which you have defined now. Yeah, so from the physical properties and the linear elastic properties, you can just double click on the properties which you want to assign. So for this, I want to assign the Young's modulus as 2 into e raised to 11. If you're considering megapascal, it is 2 into 10 raised to 5. Poisson's ratio, I'll take it as 0.28 at the moment for the stainless steel reference. And the density is 7800. Okay, you can just double click on the density here. So once you do it, you can able to assign the value. So as I said, it is kg per meter cube. 7800, you can define it. Yep, so once you add your static material data, so you can directly switch back to the project at the top menu. Okay, so whatever the material we have created, it will be saved into account, and you can use it. So I'll switch to the project, and I'll import the model now. So the tuning fork is the step file which I'm going to work on, right? Yeah. So geometry, I need to import it. Just simply right click on it, use browse, and from the desktop I need this tuning fork step file. Just use it. As you could see the green check, it shows the model got imported. So I need to deal with the modeling. So for that, you just need to double click on the model or right click and edit to switch to the modeling workbench. Okay, so once you do that, it will give you the one more new tab. So over there you need to work on these all the steps. Okay, and SolidWorks, it is a single user interface, and in Abaqus also it is a single one. So here you'll have the different tabs to work on it. Okay, this is the mechanical workbench tab. Okay, this is a new window here. So on this you need to work on. So the model will be imported. Yep. So the initial step is to deal with the geometry. Okay, as you could see, this is the geometry. You can align it by using the mouse right click and middle cursor buttons. So first thing is to deal with the geometry. I'll assign the material. So these are the solutions which I'm not looking for at the moment. So I'm dealing with the model analysis. So this is the tuning fork. You can directly go to this detail stage, and here you can assign the steel at the bottom. As you could see, the material which I had created, it is there. Once you assign it, next thing is to deal with the mesh. So by default I'll use the program controlled. If you want to deal with the sizing, just expand it, and at the bottom the minimum edge length or the default size you can specify. I'll take it one and just I'll mesh it, and here you could see this is the mesh, but this is not fine enough. I'll go ahead with the element order, that is quadratic. Then try to mesh it again. Yeah, so this is also not that much fine, so I might need to deal with the relevant center, that is fine, and even the, okay, let me see this. Yeah, this is fine, but still I need to refine it. As you could see at the top and the at the curvature regions, it is not meshed properly. So I'll just change the span angle center to 5, and then size function to curvature. Okay, now I'll see. So now this will work, I believe. Yep, so this is fine, no issues. So you can even reduce the size, but for me it is okay at the moment. This is a solution tab. Okay, first I need to deal with the analysis settings. So I need the number of mode should be 10. Okay, that is the frequency range, the 10. Okay, so I'll just run the study. So once you do it, all the 10 mode shapes will be created. Yep, to extract them, you need to use this graphical annotations tab. The bottom, you need to drag it up. Before that, I may need to check the solutions, and I need to take the displacement results. So what I'll do is I'll go to inserts and deformation. I'll select the total deformation. Okay, so I'll just evaluate it, or we can solve it at the moment, and you could see here you'll get all the frequency ranges. So as you could see, even at the fourth mode, it has the same frequency values, that is 443 hertz. Just select all, create mode shapes. So all the mode shapes we created. So for your information, you can even evaluate this again to check all the uh, modes. So for that, I'll select all, or you can simply first go to solutions and evaluate. Okay, yep, so directly switch to the 10th one. It is same thing, I think. Yeah, 4800, as you could see, no more changes there, and remaining will be the same. So at the moment I'm concerned of only the fourth one. So that is 443 hertz here. Okay, yeah, so as you could see, the natural frequency of this tuning fork, it is 450 hertz and Ansys as well. So now let's see, this is the animation. This animations are just approximation, so we don't need to rely on this. These are just the modes. Okay, Yep, so I'll do the same analysis on the one more software, that is Abaqus now. Okay, let me just switch to the platform. Yeah, so I'll go to open. So this time I'm going to import the model, that is part. So I'm looking for the step file. You can filter it. Okay, it should be in desktop, the tuning fork step file. Just import it here. The part name is same, just click on OK. The model will be imported. Okay, so it shows the curvature regions that I need to apply the fine mesh. I'll do it later. So you can use the modes as well as the part dialog box in the chart only. That is free. So first thing is I need to assign the section. So select whole model, just click on done. So here I may need to assign the selection. So it is solid model. So material I need to assign, just select this, and general I need to assign the density 7.8 into e raised to 9. I'll apply, and here elastic, it should be in megapascals. I think it's between pascals. Okay, and it should be in, yeah, percentage ratio is constant 0.28. It is megapascals. Here the unit system plays very important role. Okay, so while assigning the unit system, you may need to take care of each and everything. Okay, the sizing I'll take it 0.5 and just apply, click OK, and I'll consider the tetrahedral mesh. I'll just run this. You need to remember this Abaqus doesn't have the by default unit system. We need to refer the SI unit system, and how you're gonna consider the units, that matters a lot. So if you're considering the SI units, you need to take the SI units everywhere. You should not change. Okay. Yeah, I need to assign the assembly part or assigned, and the step I need to assign. Very important stage here. You need to change to linear perturbation. So I'm looking for the frequency. Here I'll select the solver as Lanco's eigenvalue solver. The range should be 10. Okay, frequency range up to 10 modes I need. You can select it, and even you can define the range, but I don't want at the moment. Okay. Yep. So next thing is to deal with the interactions not needed, the loading, no fixtures needed actually. Okay, I'll just select the symmetry and hold the shift, select these two faces, click on done. Okay, the last one, so it will just constrain all the modes. Yep, so job I need to submit. I'll create the job, you can name it. Okay, it is frequency. Don't include the space and all here, or else you will get the error, remember that. So once you're done with that, you can directly go to the job, but still it is not created. I think I'd switch somewhere else. Just creating step 2. I'm gonna click somewhere else and cancel it. Yeah, I'll switch to module, and it is job. Yeah, it is not yet complete. Just click on OK to complete it. Yeah, now you could see the frequency job is created. Simply submit it at the moment. Yeah, so what I was telling is the unit system. So it will take the default unit system which you are considering. If you're considering meters into default length, the unit system will differ. Or if you're considering the the unit system will differ. Very important thing needs to be noted. Okay, if you're considering meter, it should be in pascals. Okay, that is uh, any number into e raised to 11. Let's say I'm considering 2, right? 200 megapascal, so it is 2 into e raised to 11. So if you're considering millimeters, it should be in megapascals, that is 2 into 10 raised to 5. Okay, and the density should be in kg per meter cube for meter unit system. If you're considering millimeters, it should be in ton per millimeter cube. Okay, so at the moment I had taken it into millimeters, so it should be 10 raised to 5 megapascal, and it should be the density should be in uh, 7.8 into 10 raised to minus 9. So conversion to kg to ton is 10 raised to minus 11. Remember that. If it is 7,800, 9.8 into 10 raised to minus 9 will be the unit conversion. So very important factors to be considered here. Okay. Yeah. So the software will take few minutes to just run these all the steps which we have given. So I kindly refer you to remember these unit system considerations. Okay. Meters, if you're considering, it is Pascal and kg per meter cube. If you're considering millimeters into account, megapascal and uh, ton by millimeter cube. Okay. In short, megapascal, ton. Okay. Meter, pascal, kg. Yep. So job is completed. You can switch to the visualize mode, that is module. Okay. And first, if I just click on this, you'll get the ODB option. So for that, you need to open the location. So this is the location which I had defined it in temp directory. Yeah. So now I'm looking for the results. So you could see this is the date and time which I had created the study and the analysis results and report. So here, if you want to check the number of frequencies list, you need to switch to the results and the step/frame. So here you could get all the results. So for this 443 here again, the last one is 4,804 here as well. So this is same in all the three softwares. So you can switch to the results displacement tab. You could see the it is not uniform. I'll just take it as uniform, the scale deformation. Okay. Now you can animate this. For that you can orient however you want. But in short, so I'll reduce the speed here. Yep. So in short, you got the natural frequency of the tuning fork 443 hertz on an average in all the three softwares. Okay. So this analysis is strictly educational. Okay. And here I just want to showcase how you can work on all the three softwares and how to get the results same. Sometimes people feel like the software is too difficult, I cannot work on the software and all. That is not the case. Okay. Yep. So thank you all. In short, we have covered the frequency analysis on tuning fork on all the three softwares, that is Abaqus, SolidWorks and Ansys. And we have concluded that the natural frequency of the tuning fork will be validated virtually for 443 hertz for my model which I had considered. Okay. Yep. Thank you all. Stay tuned. Bye everyone.